Hello students, welcome back. Now let's begin the main topic of lesson 14, linear regression. We're going to do it in two parts. First, the point estimation. Here are some visualizations of linear regression. Some temperature example. Let's see, for given X value, that is given temperature in Dallas, what is the best point estimate or best point prediction of New York temperature? This program is randomized, so let me run it again. Dots are so tightly packed, it's really difficult to see what is going on. So let's go to Los Angeles. Okay, that's better. All right. So given Dallas temperature, say for example around 75, the best point prediction is right on the line here, the regression line. But once you make that prediction, the observed temperature may be a little bit different in New York, or excuse me, in Los Angeles. Suppose that it's actually down here. Then what's the prediction error? That's the vertical difference. Make sense? The regression prediction error is the vertical distance, because the regression prediction will be right on the line, the regression line. For example, if Dallas temperature is about 60 here, then the best point estimation is on the line. The best point estimation, the best point prediction for Los Angeles temperature is right on the line of best fit. But actual temperature of southern Los Angeles may be a bit lower. So that difference is the prediction error. This program is randomized, so let's run it again. And we have, a little bit difficult to see because the line segments are so small. Okay, all right. Here in this case, the Dallas temperature turns out to be around 69. Yeah. We make this regression prediction right on the line. And observed temperature turns out to be this high, and this vertical distance is the prediction error. What we want to do is find out a line that will minimize the sum of all those vertical distances, sum of all those, or more precisely speaking, averages of all those prediction errors. For San Francisco, again the same thing. The vertical distance is the prediction error. Let's go back to Dallas. Yeah, dots are so tightly packed, so I cannot see a lot of vertical distances, no matter how many times I run this randomized program. But if I go back down here, then I'll be able to see, vertical distances. All right. Now, that was some motivating examples. Now, the question is, how do you find the line of best fit? I mean, if the equation is given like this by computer, that's great. I can plug in X value, say 85, plug it here and do your computation and you get your Y value. That's the Y value on the line when X is given as, say, 85. But how do you find this equation with line to begin with? That's where these two formulae are coming into play. The first formula is based upon the slope point equation of the line. Y equals to slope times, let's see, Y equals to slope x minus x naught plus y naught. So the line runs through the point x0, y0 and slope m. You see? Here, the slope turns out to be this quantity, r sy over sx, and then running through the average points x bar comma y bar. That makes perfect sense because x bar is x mean and y bar is y mean. So you can use the slope point equation like this, or you can use this formula in the textbook. Slope-intercept equation, y equals to b0 plus b1x, and b1, the slope is, well, the same slope formula here, r sy over sx, and then b0, it turns out like this, y bar minus b1x bar, which is actually obtained from, setting this one as b1 and then breaking up. As a matter of fact, I think there is, no, not really, there's no visualization or there's no proof here, so okay, let's go ahead and do that. From here, this one is b1, right? All right, and then break it up. And then y bar, which was there before, and then b1 times x bar. So this is b0, as I have over here. So that's b0, and b1 is the same slope, r sy over sx. Maybe I should have increased the font. There are fractions and indices. Okay, whether you use this or use that, it's the same thing. In 1680, students didn't understand the difference between the two, so I had to go through both. But here in 3000 level, I assume everybody knows the equivalence between this and that. The slope point equation of the line versus slope intercept equation of the line. Okay, we're going to use those regression line formulae to get some regression prediction done. And the tradition is used hat notation for the prediction value. So here we have no hat because this is equation of the line. And from here, once given x value, you find out regression prediction using this. You use hat. From here again, this is the equation of the line, so there's no hat. But once you put in x value and get your regression prediction, traditionally you use hat. Okay, keep those in your mind, and then let's go ahead and do some problem here. And okay, find the best point prediction of the monthly average high temperature of New York when that of Dallas is 89.6 degrees Fahrenheit. Let's see, Dallas and New York, and here we have scatter plot, and also yes, we have x bar value, y bar value, we have everything. All right, okay, here's the slope point equation of the line. And x bar, y bar is the average point right here. And we are doing regression predictions, so in the end we have to have y hat. And the x value I'm plugging in is 89.6. Now, how about all other values? Well, x bar is Dallas average, 76.4419. And y bar is New York average, 62.1367. Now let's go to the slope formula there. R sy over sx. Okay, what's R? The correlation coefficient, which is 0.959292, approximately speaking, of course. And sy is the standard deviation of y. 16.6937. Sx is down here, 14.4631. Standard deviation of Dallas. All I have to do is to calculate all this using a calculating tool, either handheld calculator, but I have Mathematica here, so let me use Mathematica. So we have 76 point something. So 76.7 degrees Fahrenheit, and that's my solution. Alright, I use slope point equation, point x bar comma y bar, and slope is r sy over sx. Okay, let's go to the next problem. Find the best prediction of monthly average high temperature of Dallas when that of New York is 76.7 degrees. Oh, wait a minute, Dallas is 89.6, then New York is 76.7, so we have to go back to 89.6. No, not really. You see, here we have the best point prediction, 76.7. And the real temperature may be much higher or much lower, or a little higher or a little lower. It can be anything, actually. So this is not really pair 89.6, 76.7. So if I start from 76.7, I'm going to get the best point prediction, and I'm going to get something higher or something lower, whatever, and that's maybe 89.6. So the pain point. So the best point prediction is not likely to be 89.6, but it's going to be much closer to the average temperature, actually. You'll see. Let's go ahead and do this. All right. Now I'm plugging in 76.7 degrees because that's given. And if I run like this, 62.4225, so about 62.4 degrees. Is this right? Same regression line formula, which proved to be correct, but I plugged in 76.7 degrees now and got 62.4. Did I get it right? I see this kind of answer a lot, especially in 1680 class. The answer is no, not really, but before correcting it, use your common sense. New York is 76.7 degrees and Dallas is cooler than New York? Doesn't make sense. Previously, 89.6 versus 76.7, Dallas is much warmer, and that makes much more sense because, look at the latitude and everything. This doesn't make much sense. Also, what is the average Dallas temperature? Average Dallas temperature is, 76 point something. Average New York temperature is 62 point something. So New York is above average. How did I end up with below average in Dallas? Nothing makes sense. Okay, X is 76.7, that's all right. But all the other things must be wrong. So how do you make it right? Well, let's see. Let's copy and paste, and let's start from there. Expand the font. And then it's regression prediction, so it had. And then I'm going to plug in 76.7, all right? Now, what's x bar? X bar is not 76.44. No, it's not right, because it used to be x, but I just plug in New York temperature in place of x, right? Because this is regression formula to find out y when x is known. So x is this value. So as a conclusion, we have to switch x and y. You see, we know x and we want to find out y. This time we know New York and we want to find out Dallas. So we have the other way around. So x value is now New York, 76.7. And x bar is New York average, 62.1367. Y bar is average for something we want to find out, is Dallas. Okay, all right. Now let's go to slope. R, no change there. It's commutative, 0.959292, all right. And SY, standard deviation for Dallas or New York? For Dallas. Dallas is Y. We're going to find out Dallas. So this is 14.4631. And then finally, this one goes down, 16.6937. All right. Nothing is accurate in statistics, so let me change this into approximate equality sign. And then this one, if I calculate, 88 point something. So about 88.5. Looks like that's what I'm getting, if I did not make any mistake. So this is wrong, so no need for that. And then here, Dallas is x, New York is y, according to this picture here. But we have to switch x and y. So x bar becomes y bar. Y bar becomes x bar. So far so good. Now Sx becomes Sy, Sy becomes Sx, and R stays the same. Looks good. So it looks like I'm gonna get 88.5. Is that really true? Let me open up the solution. Yes, 88.5. That is correct. Well, much better solution is here, so I don't need this any longer. Let me remove it. And again, I don't need this anymore. Let me remove it. Much better solution is here already. Yeah, switch x and y. Now New York is x and Dallas is y. Make sense? Regression prediction formula is to find out y value when x is known. You want to go the other way around? We have to switch x and y.